Great. So thanks so much for having me. I'm Nalini. I'm a PhD student at MIT, and I'm going to spend the next little while telling you about my work on incorporating different levels of information about imaging physics into deep learning models for MRI reconstruction. So as many of you know, MRI is an extremely powerful imaging modality. It's used really commonly in clinical applications and for researching and understanding the human body. We saw some examples of that in the previous talk. And in practice, the way MRI is acquired is in Fourier space. So in order to get the image, which we've shown on the slide, you first acquire what I'll call K-space data, and that's shown on the bottom of the slide. So we assume that there's some underlying image X. This is the thing that you're trying to see ultimately. And inside of the MRI, there's what we'll call different coils, and you can think of these as sort of sensing different parts of the image with different strengths. So in our imaging model, we have this underlying image X. It's sensed by these different coils CI, which we've written here as a matrix multiplication. And then in practice, the thing that the scanner spits out is the Fourier transform of that result. So overall, we have this forward model, which is the equation at the bottom of the slide, which describes how we get the measurements that we get from the scanner, that's Y, from the underlying image X, which we're trying to recover. And so in practice, we get these measurements Y off the scanner, and then we have to reconstruct this image, which means we need to do something to get back the image X from the measurements Y. There are a couple of challenges with MRI, and so the ones I'm going to focus on in this talk are that MRI is a pretty slow imaging modality, so it can take several minutes or tens of minutes to acquire a single scan. And it's also an imaging modality that, as a result, is really susceptible to motion. So if you have somebody in the scanner for so long, it's highly likely that they're going to move around even just a little bit, and that can really throw off the images that you get. So one way to speed up the scan to avoid these artifacts is to just acquire fewer measurements. So in practice, it takes some amount of time to acquire each line of measurements in the K-space, which I've shown on the slide. And so if you want to make the scan faster, you can just acquire fewer lines in K-space. And so I've shown that here on the slide, and we've denoted it with this undersampling operator U. And you can think of U as just this selector matrix, which describes which points you are and aren't acquiring in K-space. And so, of course, if you do this, you have a much faster scan. But the problem is that your image, which you reconstruct, looks a lot worse. And you can see there's a lot of artifacts in that image that's on the slide. And even if you do this, there might still be some residual motion artifacts. And so the model here is something like this. We assume that you're going through K-space, sort of going through these individual lines, and you're acquiring them on the scanner. And while you're doing that, the subject is moving through a couple of different motion states S. So for each motion state S, we have a motion parameter M. M operates on our object X, and then we have the standard forward imaging model. And you can see that if you incorporate motion into this process, you get even further worse images compared to the previous examples. And this setup is even more challenging than the previous examples because we don't fully know the forward model in this case. So in the undersampled case and the standard imaging case, we can exactly write down that equation on the bottom of the slide. But in the case when we have this motion corruption, we in general don't know what the motion parameters are. And so we can't even fully specify what this model is for how we get the measurements from the underlying image. So this talk is going to be about how we can incorporate different levels of information about how measurements are generated from the underlying image when we're designing neural networks to do MRI reconstruction. So we're going to talk about this both in the case where you fully know the forward model, which is those left two cases on the slide, and in the case when there's some things that we don't know about the forward model, which is the motion corrupted case on the right. And so there's really been a lot of previous work on all of these different kinds of problems. And in particular, there's been several decades worth of classical approaches that use sort of optimization techniques in order to solve this reconstruction problem. I'm not going to go into detail about each individual approach, but at a high level, what you can think of these techniques as doing is they set up some objective function, which is based on the forward imaging model, which we specified on the previous slide. And then they search over the space of images to find an image which is consistent with the measurement that was acquired and with the forward model, which we think is describing the data generation process. More recently, there's been a lot of interest in using deep learning to solve this problem, both because inference times are really fast. So instead of having to do these long searches from the classical approaches, you can get a pretty good reconstruction on the order of a couple of milliseconds. And because empirically, there's been a lot of results that you really get high quality reconstructions. And so we're going to bin these deep learning approaches into roughly 3 different categories of strategies based on how well they incorporate information about the forward imaging model. So the simplest way to do this is to just not incorporate information about the forward imaging model at all. So here we'll assume that we have some data set of paired images where we have corrupted images and also really high quality images to reconstruct. And what you do is you take your network, you feed it pairs of the corrupted and the corrected images, and you hope that your network will learn how to reconstruct the corrected images from the corrupted images. And there's no information here, once again, about sort of how the measurements are generated from the underlying image. A second set of approaches uses what I'll call a hard data consistency constraint. And so the idea here is that you want to take advantage of the fact that there are some locations in K-space where you know what the measurements should be. So just as before, you train a network to do some reconstruction, but then what you do is you look at the K-space that corresponds to your reconstructed image. And at the points in K-space where you know what data you acquired off the scanner, you just replace those points in K-space with the data that you acquired. And so now you sort of know for sure that the result of your reconstruction is going to be consistent with the measurements that you got in the imaging process. The third bucket of approaches I'll describe as iterative or optimization based. And so here what you do is you start off with some corrupted image, you feed it into a network, and you can think of these convolutional layers as doing updates based on some sort of implicit prior on what the reconstructed images should look like. And then you perform one step of a classical optimization-based approach to doing reconstruction. And what this step does is it encourages consistency with the forward model, which we think we know about the imaging process. And you repeat these series of two steps multiple times over the course of the network. And at the end of it, you've produced a final reconstruction with which you hope is both consistent with your implicit prior and which is consistent with the process that was used to generate the data. And so this talk is sort of orthogonal to these three different buckets of approaches. And we're going to talk about different ways that we can incorporate information about the forward imaging model into all of these types of neural networks. So in the first half of the talk, I'm going to focus on the design of the core network layers. So if you think about these three different setups for how to do reconstruction, for all of them, I'm going to describe how we can use the forward imaging model to inspire the design of the individual layers themselves in the context of these three different architectures. And then in the second half of the talk, I'm going to talk about how we can use the forward imaging model to inspire the design of the overall network architecture and of the inference procedure which is used, focusing specifically on the case where we only partially know the forward model, which is the motion corruption case. So if you think about the three buckets of strategies I described earlier, in the first case, we haven't incorporated any information about the forward imaging model. We're just training a standard supervised setup. And the second two cases require that we fully know what the forward model is. So in particular, if you want to just copy and paste data that you've acquired into your final output, you can't do that in the motion corrupted case because we know that some of that data is wrong. It's motion corrupted. And if you want to do this optimization step-based approach, which is on the bottom of the slide, you really can't do that either in the motion corruption case because we don't know what the motion parameters are. And so we can't form the forward model. So in this part of the talk, I'm going to describe how we can deal with sort of this slight ambiguity and design a method which incorporates whatever information we do have about the forward model while leaving room for solving for the parameters which we don't know. But in the first part of the talk, I'm going to focus on the design of these core network layers. And the key idea here is very simple. So we're just going to use what I'll call joint layers, which incorporate convolutions both in image space and in K-space. And to motivate this, I'm going to show you a really hand-wavy visualization just to give some intuition of what we're trying to capture. And then we'll show in the experiments how well this really works. So the visualization is like this. What we've done here is we've taken a really large data set of brain MRIs from the ADNI data set, and we're visualizing the correlation structure across that large data set of images. So in this visualization, there's a single pixel of interest, which is the pixel at the center of that circle. And then all of the other pixels are colored based on the correlation across the entire data set. So if you see a pixel that's colored red, this means that across the entire data set, pixels at that location have a high positive correlation with the pixels at the circle of interest. If you see a white pixel, that means there's zero correlation across the data set. And if you see a blue pixel, that means there's a negative correlation across the data set. And so we can move the pixel of interest around. So we're looking at different locations in these images. And you can see that the global correlation structure is extremely different for different locations in the image. But there's one thing that remains pretty consistent. And that's there's always at least this really small sort of local dark red patch. And if you think about it, this is a pretty intuitive result. So all this is saying is that locally, we expect pixels that are next to each other to be highly correlated with each other. So pixels that are next to each other are likely to be similar, probably because they belong to the same structure in the image. And this is the correlation that we think standard image space convolutions are typically capturing. So you normally have these local convolutional filters, which operate on really small patches and capture this correlation structure. So now what we can do is we can visualize this correlation structure for the corresponding k-space data, which you'll remember is in Fourier space. And probably the first thing that jumps out to you is that there's this sort of rotational symmetry where we have this symmetry at 180 degrees, and there's kind of two blobs that are rotating in tandem with each other. That's actually not what I want to focus on here. That's an artifact of the fact that we're taking Fourier transforms of real valued images. And instead, what I want to focus on is, if you look within this tiny circle, you can see also there's these really strong patches of local correlations. So these are pretty different from the pure image space correlations. You can see there's sort of this checkerboard pattern, and there's both strong positive and negative correlations. And the idea is, in addition to capturing the strong local correlations in image space, we want to capture these correlations in k-space as well with our neural network architecture. So to that end, we're going to define two really flexible sort of task-independent convolutional layer structures, and we're going to show them in three different experimental setups. So first, I'll show that in this really simple case, where you don't have any information about the forward imaging model, you can just drop in these joint layers into these setups and get really good reconstruction results. Next, I'll show that even if you incorporate some information about the forward imaging model, so you have this hard data consistency constraint, replacing image space convolutions with our joint layers still provides improvements to performance. And then finally, I'm going to show that if you have these unrolled or optimization-based networks, you can also replace image space convolution layers with our joint layers, and we'll see improvements in the convergence during the training process of these networks. So we'll get started and start by defining these layers. At a high level, you can think of the main difference between the two different versions of these joint layers and the way that the types of convolutions are composed. So here's a diagram of a network, and we'll focus on an individual layer within the network. And this is one version of our joint layer, which I'll call an alternating layer. And so here, the high level idea is that you apply these convolutions in series. So you start off with some image representation which exists in frequency space or in k-space, that's shown in red. And then you apply a convolution in the frequency space. You do an inverse Fourier transform to move over to the image space, and then you apply a convolution in the image space there. And then you repeat this process down over the course of the network until you get your final reconstruction. This is in contrast to a different architecture, which I'll call interleaved. And so here, the high level idea is that you're going to do these convolutions in parallel. So now for each layer in the network, you'll maintain two sets of representations, one that lives in frequency space and one that lives in image space. And I'll note that these representations are not constrained to be related by the Fourier transform. So we let these sort of vary independently in the spaces that they live in. Then we learn linear combinations of the representations in both spaces, and we apply convolutions in both spaces and then repeat this process over the course of the network. And I see there's a question in the Q&A. Okay, so the question says, how is occlusion by other vessel or body parts handled? I think this is for the visualization. So here we're visualizing 2D slices within a 3D volume. So in practice, there's no occlusion here. Like you would be able to see the other structures if you looked at other slices within the same volume. Okay. So we'll move on to the first experiment, which is the most simple case where we have just these networks that sort of have no bells and whistles to the architecture. They're just a series of convolutional layers. And what we're going to do is we're going to just replace sort of typical image space convolutions with our joint layers, which I just described. And we'll demonstrate this on 2D slices from T1 weighted brain MRIs. We have a set of training, validation, and test slices, and we're going to simulate a bunch of different artifacts. And I'll note that for this section of the talk, these experiments are very simulated, sort of so that we can control the quality of the artifacts, but later in the talk, I'll show results on some more realistic data. So we simulate 4 different types of artifacts. We simulate motion, really heavy noise, undersampling, and then we also simulate a combined artifact where we have motion occurring over the course of an undersampled acquisition. And so here's a sample result. The first column shows the ground truth image that we're trying to reconstruct. And the second column shows, in this case, a motion corrupted input. So this is the thing that we're saying we would have gotten off of this scanner. And we'll also visualize a zoomed in patch, so you can see some of the details of the image, a difference image for that zoomed in patch, and then the k-space data, which is corresponding to the reconstruction. Next, we can look at these two baselines. And so these are the results of networks which operate just in one of the two spaces. So on the left, we have the result from a network which is trained to operate just in K-space. And on the right, we have the result from a network which operates just in the image space. And you can see for this really challenging motion corrupted task, you really lose a lot of the details in the image. So they're either blurred or sort of shifted, and it's hard to make out some of the really key structures. And we can compare that to the results from the two versions of our joint layers. And these are definitely not perfect reconstructions, but you can definitely see some of the structures with a lot higher detail than you could in the two baseline methods. And I've shown this just for a single example here, but we find that this result holds extremely consistently across tasks and examples. So here I'm showing some quantitative results. Each panel corresponds to one different corruption type. And the y-axis here is SSIM, which is just a measure of the quality of the reconstruction, and you want to be higher up on this plot. That means you have a sort of more faithful reconstruction. And so you can see that for every single task, for almost every single subject, the reconstructions from our joint layers, which are shown in purple, outperform the reconstructions from the single space networks in blue and red. Another question. And the question is, can we implement this method in real time by attaching EEG to the head? I'm not sure I understand about the connection to EEG. Maybe you can clarify that in the comments. For MRI in particular, the inference times here are about on the scale of a couple hundred milliseconds. So we probably would need to get that down to be a little bit faster if we wanted to sort of adjust the scan in real time. But if you just are doing a scan and then want to look at the reconstruction, it should be more or less instantaneous from the point of view of the user. And then the next question is, would it be preferable to incorporate ordinary cameras to recover the motion directly? Yeah, so this is a great question. There's definitely people who are working on stuff like this. I think I'll focus on this a little bit more in the second half of the talk, which is focused on motion. The short answer is that it's definitely helpful to incorporate motion information, but there's challenges in incorporating devices which measure the motion inside of the MRI, which has a really strong magnet. And also, depending on the type of motion you have, a device like a camera might or might not be able to measure it. So, for example, some people are interested in fetal motion. If you just have a camera measuring the outside of the body, you won't be able to see that with a standard camera. Okay, so we'll move on to the second set of experiments. And so now we have a slightly more complicated architecture where it's the same setup as before, but instead of just taking the output of the neural network, for the undersampled case where we think that the data from the scanner is correct, we'll replace the data at the locations where we've acquired it with the data that we got off of the scanner. And we'll demonstrate these results on a similar data set, but now we're going to focus on the undersampling case, and we're going to look at three different types of undersampling. So first, we're going to look at two undersampling setups, which are really standard. There's a central region in Fourier space, which contains sort of the highest signal energy for these images, and that region is fully sampled, and then we undersample on the regions external to that. And then we'll also sort of stress test our method with a completely random undersampling pattern. This isn't a typical undersampling pattern that would be used on an MR scanner today, but this is sort of looking forward to applications that other people are working on, where people are also trying to use machine learning techniques to optimize the undersampling pattern that's learned in real time on the scanner. And so this is sort of a stress test to see whether our reconstruction method could handle these really highly variable undersampling patterns. So here are results for those experiments. And what we're doing here now is comparing our method, which is shown in purple, the two bars to the right of each plot, with state-of-the-art networks, which are shown on the left parts of each plot. And all of these methods incorporate the data consistency constraint at the end, where you copy and paste the values. So this comparison is really isolating the effect of our joint layers. And if you look at the first two columns, which are the more standard undersampling setups, you can see that our method performs roughly on par with the state-of-the-art networks. We're not really arguing that we're beating the state-of-the-art there. But then on the right, if you look at the more challenging undersampling setup, where we have sort of random undersampling patterns in each case, you can see that we do outperform the state-of-the-art networks. All right, and for this third set of experiments, we're going to focus on these unrolled networks, which incorporate optimization steps into the structure of the neural network. And we're going to focus on sort of a really standard version of this for MR reconstruction, which is called modal. And what modal does is that you can think of the whole forward imaging process as described by this A matrix. And modal performs conjugate gradient-based update at each of those optimization steps in the network. And if you're not familiar with conjugate gradients, that's fine. You can just abstract this to thinking of sort of one step of a standard optimization-based procedure. So what we do in this experiment is we take this exact same setup from the original modal paper, and we take the image space convolutions which they apply and replace them with our joint layers. We do this on the same data that's used to train those networks. And so now we're looking at 3D multi-coil T2 cube MR acquisitions, and this is sort of a very realistic MR undersampling setup. And we simulate 6x undersampling with a variable density sampling mask. So this is sort of a standard undersampling pattern that was also used by the original modal work. In practice, there's this detail noted by the modal authors. So they're unable to train their network end to end. And instead what they do is they pre-train one iteration of this network, copy and paste the weights that they've learned into a 5-iteration version of the network, and then they fine-tune this 5-iteration version of the network. In practice, we find that with our joint networks, we don't need to do this pre-training. We just directly train the network with 5 iterations, and these are the 2 versions of the networks that we compare. So here's the training and the validation curves for the 2 setups. We'll focus on the darker lines in blue and purple, and blue is sort of the standard setup from the original authors, and purple is our improvement on this, where we incorporate our joint layers. And you can see that at the end of the training process, both methods do comparably. So both methods achieve approximately the same reconstruction quality, but you can see that our method in purple gets there a lot faster. And we can confirm this qualitatively. So here's the reconstructions at the end of the training process. You can see that both methods provide pretty good quality reconstructions. But now if we look roughly a 1/10 of the way through the training process, our method is basically at the final reconstruction quality, while the pure image space convolutional network is really noisy and provides artifacted reconstructions. We can also quantify the time savings resulting from this. So if you take into account the fact that we don't need to pre-train our version of the network, we get roughly an order of magnitude speed up in training these networks. Okay, and there's a question about would it be possible to account for possible motion, but not enforce that they match exactly, but that the change can be explained by motion? Yes, I think I'll talk about this a bit more in the second half of the talk, which is focused on motion. And feel free to ask clarifying questions then if I haven't covered this. Okay, so to summarize this first part of the talk, what we've shown here is that incorporating Fourier space representations into neural networks improves the performance and the optimization behavior of those networks when they're used for MR reconstruction. So we proposed 2 core layer structure designs, and they're really easy to implement. So we have an open source implementation of these, but they're also just really easy for you to implement yourself. They're both just a couple of lines in your favorite machine learning library. And they're really modular sort of drop-in replacements for image space convolutions. Experimentally, we've shown that they improve reconstruction across a wide variety of tasks. And we've also shown that they're compatible with a really wide range of network architectures. So for all 3 of the buckets of sort of types of previous work I described earlier, we've shown that you can just drop in our layers as a replacement and you'll get an improvement in either performance or in the speed of the training. So with that, we'll move to this next part of the talk, which is focused a bit more on motion correction. And I'm going to show how we can use a partially known forward model to inspire the design of the network architecture and inference procedure, focusing on this motion corruption case. So just to recap, we're assuming that we have this forward model. Here I've described it with the A matrix. We'll go into a bit more detail about it later. And we have our image X, which is the thing that we're trying to recover. It goes through our forward model A, and then it gives us these measurements Y. So if we assume that this noise term epsilon is complex valued Gaussian noise, we can write out this expression for the posterior probability of the image, given the measurements which we acquired. And if you look at this expression, there's basically 2 terms of interest. So first, there's this term, which I'll describe as the data consistency loss. And what this says is, if you start off with your image X and you pass it through your forward model, how close is that to the measurements which you actually acquired off of the scanner? The second term is the prior, which just describes for a particular image X, how likely is that image in general? Like, is this a realistic image, or is it something that we think doesn't look like a realistic image? For motion in particular, the forward model is shown on the slide. So here what we're assuming is we're just going to model rigid motion. And so R and T are rigid rotations and translations, which affect the object of interest. So for each segment S in the course of the acquisition, there's a different rotation and translation which characterizes the object. And then we have the standard MRI forward imaging model as before. So we have our quell sensitivities, the Fourier transform, and then we have the undersampling operator, which describes which section of K-space was acquired during this particular sort of motion state of the object. And as I mentioned earlier, the really challenging part about this problem is that these motion parameters, which form the rotation and the translation matrix, are unknown in general. So while you could incorporate a device to measure these, we're going to focus on the really challenging but standard case where we don't have any information about what these parameters are. And this is challenging for two reasons. First, it's unknown, as we described. So from one example to the next, we don't know how to get what the motion parameters are. But also, this means that if you have a large data set of images, your A operator is actually changing from one image to the next. So for example, if you have a data set of motion corrupted MRs, and you're trying to train a network on that whole collection of images, you need to account for the fact that this forward model is different for each of the pairs that you train your network with. So if we think about these previous buckets of prior work, in the first case, what we're doing is just assuming that the network can handle that variability in the forward imaging operator. So you could train your network with just a bunch of pairs of motion corrupted and motion corrected images, but you're sort of leaving it up to the network to figure out what the forward model is and to handle variability in that forward model. The other two strategies, as we described earlier, don't really work in this motion corrupted case. We can't just copy and paste the measurements into the appropriate locations because we know that some of these are wrong due to the motion. And we can't do the optimization step because we can't, in order to do that, we need to be able to write down an expression for the matrix A, and we don't know what the motion parameters are. So these methods both require full knowledge of the forward model. So people in MRI have sort of recognized this, and they've developed more sophisticated approaches for doing deep learning for motion correction in MRI. And at a high level, all of these strategies involve data consistency-based searches over both the image and the motion parameters. So one approach is to use your network to just sort of initialize this search. You train a network on pairs of motion corrupted and motion corrected data that gives you sort of your first guess for what a motion-free image would look like. And then you do a classical optimization-based approach to solve both for the image and the motion parameters. The second strategy is to only use your network to describe the prior distribution. So now you have a network which tells you something about how likely a particular image is. And then for each new image, what you have to do is, again, sort of a classical search to find an image and a set of motion parameters, which are both consistent with the forward model, which are highly likely under this prior, and which give you motion parameters, which are realistic. So in both of these cases, the computational challenge is really intense because this search over both the image and the motion parameters makes the search take a long time, and often the search does not converge. So what I'm going to talk about in this section is our strategy to really dramatically reduce this optimization to a search just over the motion parameters M. And the key idea here is, again, extremely simple. It's just that you need to set up your network to be a function of both the k-space data and the motion parameters. So what we do is we have our neural network F. F takes as input the motion corrupted data Y, as well as some motion parameters M. And it produces a motion corrected reconstruction, which you can use to get your image. So in training, we need to be able to know what the motion parameters are in order to train this network. So we train this network with simulated data. We assume that we start off with some motion parameters which are known. We simulate what the corresponding motion corrupted data Y would be. And then we use that to train this network F in order to produce high quality reconstructions that are motion corrected. In practice, we do this by taking the output of the network, comparing it to a ground truth image via the SSIM loss, and then using that to update the parameters theta, which specify the neural network. So then what we do is we freeze this network, and at test time, we don't know what the motion parameters are. So at test time, we run another optimization, which allows us to search for the motion parameters M. Now, in this case, you might say, well, how can we optimize for M? We don't have any label with which to compare the network outputs. And so what we do in this case is we use a model-based data consistency loss. And so this is inspired by the probabilistic model, which I described earlier. It doesn't require any labels for our test time examples. And what we do is we start off with some estimate for the motion parameters. We run inference from the network to produce an estimate X hat. And then we pass our estimate through our forward model. Doing so gives us sort of a simulated version of the measurements, which we can compare to the true measurements, which we got off of the scanner via this data consistency loss. And then we can backpropagate this data consistency loss iteratively so that we keep updating the estimates of the motion parameters until we converge on a good estimate. In practice, the way we implement this network is with a hypernetwork. And so what this means is that our network F is actually comprised of two networks. We have the hypernetwork H, which takes as input just the motion parameters M. And then H produces the weights theta G of another network G. And G is the thing that does the reconstruction. So at a high level, you can think of this as H is producing sort of a motion parameter specific reconstruction function, which is then used to do the reconstruction. So what are the benefits of this approach? First, we've dramatically simplified the search that you need to do at test time. So we no longer need to search over images. Now we just need to do the search over the motion parameters M, and our architecture ties the motion parameters to a specific reconstruction. So we get the image for free if we find a good estimate for these motion parameters M. Second, because we have explicit estimates of the motion parameters, we can reject low quality reconstructions. So two reasons that you might get poor reconstructions are, first, you might have good estimates of the motion parameters, but your network produces a bad reconstruction, or you might just have bad estimates of the motion parameters. In either case, this data consistency loss will be high, and you can use that as a signal that you should reject the reconstruction which you've generated. So we demonstrate this on 2D slices from FLAIR FSE brain MRIs, and there's some acquisition parameters, which I've shown on the slide. For training, we have to simulate this data, and so we have a data set that we use to do this. We simulate using the forward model, which I described earlier, and we simulate really sort of dramatic motions. So we randomly sample a point during the acquisition at which we apply the motion, and we simulate translations up to 10 millimeters and rotations up to 10 degrees, which for MRI is really sort of dramatic motions to be occurring over the time scale of this imaging. And so what we do is we start off with some image X. We apply our simulated motion parameters to generate sort of the moved version of the image. We have estimates of the coil sensitivity maps, which we use to simulate what the k-space data would have been for the two different positions that the object is in. And then we combine the appropriate lines of k-space from the two different positions. So at the end of this process, what we have is data which represents what you would have gotten from the scanner if the object moved from the blue position to the red position over the course of the acquisition. We test this method on a realistic mixed data set. And so what I mean by that is that we have one slice which was generated as follows. We had one person who was in the scanner, and we scanned them twice, and we asked them to move between the two different scans, and we mix the k-space data from these two different scans. So what this is doing is it's sort of removing our motion simulation from the process. It's using real motion, but it allows us to have high quality reference scans that we can compare our results to and make sure that we're reconstructing correctly. So we'll compare our methods to 4 different baselines, and I'll group them into 2 different groups. The first I'll describe as motion naive baselines. And so these are methods which assume that you don't have access to the true motion parameters. And this is the setting that our method operates in as well. So the first of these I'll call ARC or grappa reconstruction. This is basically a classical approach to reconstruction. It doesn't do any motion correction. It's kind of the clinically used thing right now. And this just fixes undersampling artifacts and gives you a higher quality reconstruction that way. The second thing we compare to, I'll call conv, and this is sort of the most basic of the baseline architectures. It doesn't assume access to the motion parameters, and it again assumes that the network can sort of implicitly model the variability in the forward imaging model. We also have 2 baselines which are sort of upper bounds for how well we expect to do. So these I'll describe as motion aware baselines, which means that these methods both incorporate the true motion parameters in producing an estimate. So this isn't a realistic imaging scenario. We're just using this to get a sense of how close we are to the ceiling of our performance. So the first of these I'll call model-based ground truth. You can think of this as another sort of classical non-deep learning baseline. And what it does is it takes the true motion parameters and applies the effects that you would expect based on those motion parameters to the data, and then uses a non-uniform Fourier transform to perform the reconstruction. The second baseline I'll call hypernetwork ground truth. And so this is exactly the same as our method, except for instead of optimizing the motion parameters, we now just feed the ground truth motion parameters directly into this network. So here's a sample result. This is the ground truth that we're trying to reconstruct, along with a zoomed in patch. We'll show some difference images and the k-space corresponding to that ground truth image. And then here's the motion corrupted data that we're trying to fix. Here's the results from the 2 motion naive baselines. the two motion aware baselines, and then here's a reconstruction from our method. And so you can see, especially as pointed out by the yellow arrows, that our method produces really high quality reconstructions compared to the motion naive baselines. There are a bunch of artifacts which are missing in our reconstruction, and the quality of our reconstruction is really similar to the motion aware baselines, even though our method does not require access to the ground truth motion parameters. Quantitatively, we can look at this across the data set. So once again, we're looking at SSIM here, and higher is better. For context, this is just how well you do with the raw input without doing any correction. These are the results from the motion naive baselines, the motion aware baselines, and then here's two versions of the results from our method. So on the left, we have the results of our method run on our entire data set. And then on the right, I have the results of our method run on just the subset of examples where our automatic rejection criteria determined that our reconstructions were of high quality. And you can see that the results from our method in dark blue are really comparable to the motion aware baselines and outperform the motion naive baselines, even though we don't require any access to the true motion parameters. We can also look at how well our results do sort of on the basis of each individual example. And so here, what I'm doing is comparing to the two sets of motion naive baselines. And what I'm plotting is how well we're performing relative to those. So the dotted line represents the two methods being equal. And what we want is for our method to be to the right of the dotted line. This means that we're outperforming the baselines for all of these examples. And you can see that that's the case for the vast majority of the examples in the data set. And furthermore, you can see that for many of the examples where that's not the case, these are examples that are shown in red, which means that those would be sort of automatically rejected by our rejection criteria based on the data consistency loss. Finally, we can look at how well we're doing at estimating the motion parameters themselves. So this is not a measure of quality of the image, but of the motion parameters. And so we've divided our acquisition into 6 shots. Those are just sort of segments of K-space that are being acquired. And the first 4 shots are the shots that contain by far the most signal energy of these individual images. And so you can see that for those 4 shots, in almost every single case, we have essentially 0 error in estimating the motion parameters. And for the cases that we don't have 0 error, for the most part, these are again the examples which are rejected automatically by our criteria. If we look at the last 2 shots, these shots have much lower signal energy than the first 4 shots. And so you can see that we do actually a bit worse on estimating the motion parameters here, but in some sense, that's okay. We kind of expect this because these shots participate much less in the data consistency optimization I described earlier, but they also contribute less to the quality of the final reconstruction. So we're able to still get good quality images, even though we have some mistakes in estimating these subset of motion parameters. And so finally, I'll show results on the really realistic sort of mixed data set. This is where we don't have the simulation and we're using data that's straight off of the scanner. And so first, I'm showing the ground truth. This is the thing that we're trying to reconstruct. And then I'm showing the motion corrupted data. Next, these are the 2 motion naive baselines, which don't assume access to the true motion parameters. And here I'm not showing the motion aware baselines because we don't have the motion parameters in this case. We can compare those reconstructions to the results from our method. And you can see, especially as highlighted by the yellow arrows, that our method provides really sharper reconstructions without motion artifacts and is in general quite faithful to the ground truth reconstruction. So to summarize, we've shown here that networks that use both corrupted K-space data and motion parameters as input allow you to do this test time data consistency-based optimization, which lets you find good estimates for motion parameters and get a really good reconstruction. Experimentally, we've shown that this approach lets us produce really high fidelity data consistent reconstructions, and that when we don't produce good reconstructions, we can reject them automatically based off of this criteria that we've constructed. And we showed this both on simulated data and a really realistic proof of concept test example. So I'd like to thank really awesome collaborators at MIT and the Martino Center for Biomedical Imaging, which is also just sort of across the way here in Boston. And I'll conclude with this high-level takeaway, which is that if we know information about the forward MRI imaging model, we can incorporate that into networks for MRI reconstruction in multiple different ways. First, we can use it to inspire the design of the core operations that comprise the network, but we can also use it to inspire the structure of the high-level network architecture and the inference procedure that's used in order to generate estimates, especially in the motion corruption case where we don't know the full forward imaging model. But there's still a lot of work left to be done here. So we've modeled a relatively simple motion pattern here, which is rigid motion, but for a lot of different other anatomies, there's much more complicated motion that you might want to consider. So for example, if you want to do abdominal imaging or cardiac imaging or fetal imaging, there's non-rigid motion. And there's also sort of second order motion effects, which we haven't incorporated into our model. And so it's really important to extend to model those. We also would like to make these networks a lot more robust to variations in contrast and anatomy. So what I sort of glossed over in this talk is that for an MR practitioner, there's a lot of parameters you need to fine tune in sort of setting up the scan so that you can see specific structures of interest or specific areas of interest. The dream, I think, would be to develop methods which are robust to all of that. So you could just train one network and then use that on a variety of different contrasts or anatomies and get really robust reconstructions that way. And so with that, I'm happy to take any additional questions.